correctly. All right. Okay, this is your water plot, right? So if I go to 5 kilohertz, let's say I go to 5 kilohertz here. I don't know how many you can see it, but let's say I go to 5 kilohertz. This is my 5 kilohertz, right? So at 5 kilohertz, I have about, so if you look at the 5 kilo, I have about minus 9 dB gain right here, at 5 kilohertz, okay? And my phase margin, if I come here, is about minus 150 degrees, okay? Right? Now, if I this is a compensated buck. So if I now plot after compensation, right? If I plot after compensation V out 2, so let me just go ahead and plot that as well. I'm going to say so V out 2. So V out 2 is a compensated one, right? And if you want to plot the phase, that's our phase. So what we have done is improved both on the gain margin and the phase margin. Okay, so if I look at the red one, so we're still at about 5 kilohertz, and at 5 kilohertz, now I have got 41 degrees instead of minus 146. I have got 41 degrees phase margin, and I have got, and if I go here on the gain side, we're at about 0 dB gain at that point of time. It basically gives you the gain margin of 41 degrees. Okay. That essentially stabilizes your system when you have, normally the phase margin you want to have is anywhere from 40 degrees to 75 or 80 degrees or so. So this is how you do Bode plot. Now this is possible. Now this, we have used the average switch, right? Now now with this compensation technique, this buck actually can operate both in continuous conduction mode and discontinuous conduction mode. But this technique works. Once we compensate it using this average switch, the same compensator works even for discontinuous conduction mode. But theoretically, it is not correct. Practically, it works. That's an engineering approach. But as Professor Patil, pointed out, you really need a different switch for discontinuous conduction mode. But in practice, it works. Okay. So this is how we compensate. So that's how we do the Bode plot. Now, the trick here is that you need to, there are a couple of ways. First, this is the point you have to make is, where do you inject your AC stimulus? Okay, that's the first one you have to make. So this is one place where you inject AC stimulus. Now we have got L and C. L is 1 kilohenries and C is 1 kilofarad. Now these components, essentially what happens is during frequency stimulus, C gets shorted, right? So we basically have an open loop. C gets shorted, L is open, right? L is open, so basically you have open loop this way, and and this gives you better results when you're trying to do open loop transfer function.
Can't we just open the circuit there?
Well, I think in real life you cannot open a circuit because your circuit will not stabilize, right? In simulation, you can open your circuit, but one of the issue is bias point adjustment. Okay, so this L here gives you a DC bias point. So the DC bias point has to be correct for the AC analysis to run properly, right? The DC bias points means that if I have 0.5 duty cycle, that my output is 6 volts. So if your DC bias point is not correct, your simulation is not going to be correct. Yes, you can open it and run it, but the results may be slightly inaccurate. Okay, so this is safer way of doing it, so that you have a correct DC bias point. So that's how you do Bode plot.
Can we inject the AC source in the feedback path?
Yes. Yes, you can definitely inject the AC. Well, this is in the feedback path right now. You can also inject between here and here, where you take the V out. Is that where you mean?
Yes.
What you mean? Yeah. You can definitely take this source here, right, and inject it between this point and this point.
Then we will have the same result.
You'll have the same result. The only thing is you have to remember what your input is and what your output is. So when you do it in the feedback path, actually I have a slide I can show you. Alright, so here is where you have injected your source. Okay, you have placed your source right here. Right? So it goes like this and goes all the way and comes back here. So this becomes your so you are basically still plotting V out, but the signal path looks like that. Okay. Same results. Whether you put it here or there, it's the same thing.
Compensation parameters are compensation.
This is just an example. Yes, that's your feedback. That's your feedback loop. Does that make sense? Yeah? Now this is for type 1 amplifier, which will have same thing for type 2 or type 3 amplifier. See that this type 1, type 2, type 3 amplifier is only used in power electronics industry. You go to digital world, they have got much, with the DSPs you can do much more sophisticated compensation than with just this type 1, type 2, type 3 amplifiers. But anyhow, that's the story behind it. Okay, so does that answer your question? Okay, we'll come back to it. I think again.
Is that simulation available for a normal cycle by cycle also?
Mm-hmm. Yes. So you have same thing here available. So once you have compensated it, you also have cycle by cycle system here. Exactly same compensator used, and now you can run the same analysis, the same after you've compensated it, you can run the same thing. So all you have to do is switch your simulation profile to time domain, and you say, okay, let's go.
If I try to do Bode plot here, what will I get?
The AC source will not go through the switch. That's a problem.
Then I'll-
Yeah, that's a problem.
If I put AC, it's okay, it doesn't.
Yeah, AC source does. See, but the interesting part is.
Because I wanted to know what is the problem.
Yeah. The AC source just doesn't go through. Now, I think there is also the whole idea about system estimation, right? So you should be able to estimate your system if you look at your response, right? So, for example, we looked at let's see if this actually stimulated. We also have a step load here. Going. Here, Vout 3, this is a type 3 amplifier, and this one basically gives you the duty cycle command, right? And you have a limiter here, so the limiter basically compares with the PWM generator and fires up the gain drive. So exactly the same compensator used here versus used here. And the thing is, this is where we have parameterized all the, so you can use exactly the same component values as you use in the cycle by cycle simulation. Right. Now you can change the loads and see how stable your system is. Here. So in the parameter file, now all the component values here have been decided, and there are formulas in the book using a KFactor technique, which is quite easy to follow, and we'll discuss that shortly. But the KFactor technique allows you to calculate the value of your components and also calculate and also guide you as to where you want to place your poles and zeros. Okay. All right. So it is. Let's go back to DC-DC converters. You have. We follow the same. We follow the same approach in the boost converter, and here. Essentially, you have inductor here, you have switch here, and this is your so that's what you have, right? So basically, you follow the same philosophy. Try to figure out what the voltage is across the inductor, and what is your I peak, and what's your I valley. And you start with a continuous conduction mode. And again, you say, okay, average voltage across the switch, across the inductor steady state is 0. And then this is how you get the transfer ratio, right? So now the interesting part about boost is it has got nonlinear transfer ratio. It's 1 by 1 minus D. So when D is 1, theoretically, the transfer ratio is infinity. Okay, so when D is 1, this is V out can be infinity, okay, and when D is 0, you basically get the same. So if you look at the characteristic for boost, you're looking at something like this, okay, and this is basically 1. This is 2. Now this is here shows you this V switch diode right here. This is this point. Okay, and here what it shows is when your switch is off. So here's when your switch is on, right? When your switch is on, voltage here is 0. So you have a 0 voltage here. When, sorry, we have gone to the discontinuous conduction, haven't we? Okay. And then when your switch is off, you basically have V out. Because when your switch is off, this diode is conducting, so the voltage here is V out. And if you're in discontinuous conduction mode, essentially your switch voltage floats to Vn. Okay, it floats to Vn because the inductor current is 0, right? And the switch, this guy, and this is off, and this guy floats to Vn. So with this, now here is again we do the same sort of calculation, and I will not. They're easy to follow. Same logic as we used in the buck converter. You can follow the same logic, and the transfer ratio comes out to be this, and you can actually. This is the final transfer ratio in the discontinuous conduction mode. Okay. Now this equation actually is linear, right? This equation actually is linear because. So the interesting part is that the buck converter, which was linear, became nonlinear in the discontinuous conduction mode, whereas this guy actually was nonlinear and it became linear in the discontinuous conduction mode. So if you look at this equation, you can very quickly see, first of all, that 2 plus d divided by tau L divided by 2. Okay, that's what it degenerates to. And consequently, your plots in the discontinuous conduction mode are something like this. Okay. So and the salient points, now this M is also dependent on the load current. And now you have a linearity. In the discontinuous mode, you have the linearity between M and D. And for a given duty cycle, M can be larger for DCM than for PCM. So similar property as we saw in the buck case. Okay. And then we go to the transition point, boost transition point DCM, CCM. Essentially gives you the value of L critical and R critical, just like we did last time, and that seals basically the boost. This is the final values for R critical and L critical. And let's go to the simulation for the boost. So we have similar that's most important to notice. And here basically these are some of the waveforms we have. We have here L is 1 millihenry, C is 30 microfarad, R is 20 ohms, and Vn is 20 volts. Okay, and we have got, that's about it. And then waveforms look like this. You basically go 52, 39. This is your inductor current. And for average switch, you have similar results. And your similar results on the inductor side. So let's look at the boost. So boost, so you can see that how the P is hooked up, and you have A and C. Now you can take the diode out. You really don't need the diode here, but we have put it here, and it works. You should get the same results. So here we have a duty cycle of 0.5. And that means we should get twice the input voltage, right? You have input voltage of 20 volts. Get twice the input voltage. So we're going to go ahead and simulate it. Let's look at simulation profiles for 60 milliseconds. All right. So this is your I'm going to start with cycle by cycle. So let's look at the output voltage. So that's your output voltage. It settles to about 40 volts. Okay. And then if you go and look at inductor current, that's your inductor. Yeah, very ripple. Yeah, that's your inductor current. This is switching. That's your inductor current, that's your voltage. Okay. And we can see, voltage across